Oh, that's right. If you've got questions about some of the sections, you have the movies to go back to, don't you? And you can just, on that timeline at the bottom, move to wherever you need to be. Or if that movie isn't working great or the explanation wasn't great, you can also go to YouTube. Okay, so there are lots of places you can go. We were in section 3.1. We had talked about things like if you have something like negative 2 times x minus 4 squared plus 3. We had talked about that this is actually quadratic. At this point, you should be able to look at that and pretty well rough out a picture of what that looks like. What's a graph of that going to look like? Where's the vertex? Yeah. You go up 3 and over 4, or over 4 and up 3, whichever you care to do. So we're going to go 1, 2, 3, 4, and up 3. 1, 2, 3. Put a dot there. Does this parabola, how do I know it's a parabola?
Square.
It's squared. Good. Does it open up or down? Down. How did you know that? The negative. The negative out front says it opens down. Is it going to be skinny or pretty wide? It's going to be skinny because it's times 2. And there you go. There's a quick picture of it. Don't you wish that was all of the test? This will actually be on the next test. So the next test will start off with some pretty easy stuff for you. Okay. We talked about the fact that, yeah, that's not too bad to do. You can look at it, you can get the vertex, you can figure out if it opens up or if it opens down. There's all kinds of good stuff that you can get pretty quickly. We also talked about the fact that this can be converted. If you needed to get it as x squared plus x plus some number, you could FOIL this out here, multiply it by a negative 2, and then add 3, and you would get back the usual equation. Does that make sense to everybody? Are you okay with doing that? Okay. Sure. There are 2 basic forms for the quadratic. One is this really nice factored form like this. The other way that you can write the quadratic is to say, well, I'm going to have a negative 2 times something or other plus 3. This x minus 4 raised to the 2 means to FOIL it, doesn't it? Now, if we were to do x minus 4 times x minus 4, which is really what that means, what we would wind up with in here would be x squared minus 8x plus 16. Does that make sense? Okay. What would you do next to simplify this? Let's see. Please excuse my dear Aunt Sally. Do we have any parentheses laying around there? Brackets. Brackets are in the same family, right? They're part of the parentheses family. So I guess the next thing to do then would be to distribute this negative 2 times each. So it's going to give us a negative 2x squared plus 16x minus 32 plus 3. Is that looking closer to done? Which will then give you y equals a negative 2x squared plus this 16x minus 29. A second way that you could write this would be something like this. Does that look familiar to everybody? That's the way you're probably more accustomed to running into this kind of equation. Okay, so you can work it either way. Okay. Equations in this form actually do occur quite frequently depending on where you're hanging out. If you're in a physics class and you're interested in projectile motion That being something like you throw a rock up in the air, throw a ball up in the air, and it's going to go up, and it's going to come back down. And the question might be, well, how high did it go? How long is it going to take before it hits the ground? Okay. How fast is it moving? Those are all questions that could be answered about that. What you wind up doing is use an equation, and in physics, S is used for distance. And the idea here is this is going to be the distance from the ground is a negative 16 t squared. The negative 16 comes from acceleration due to gravity. Well, I suspect you're probably comfortable with the idea that gravity is going to have something to do with this, aren't you? Because every time you throw something up, where does it go? It comes right back down because of gravity. That's no big surprise. Okay? The negative 16 comes from the pull of gravity. Plus v sub 0 times t. V sub 0 is how fast is it going at the start. The little 0 means at time 0. So at the start. So v sub 0 is the initial velocity, or the velocity, for example, if you were to throw it, the very second it breaks contact with the tip of your fingers, that's the initial velocity. Plus s sub 0. S sub 0 is the initial height. Remembering that S means height. So we're going to have v sub 0, which is the initial velocity. And we're going to have S sub 0, which is the initial height. Make sense? Where did this come from? I'm not asking you to know that. You can use some calculus to get that, but I'm not worried about that in here. All I'm asking you is, does v sub 0 and s sub 0 and the fact that you can plug them into that equation make sense? Not where did the equation come from. We're not wading into that. Okay? But there's that equation. Okay, so how do you use something like this? Well, one of the examples that they provide in the book says you take a baseball and we throw a ball up. Upward at, let's say 60 feet per second from a height of, let's say 8 feet. 8 feet. How would it get to be 8 feet? Well, if you're about 6 foot tall and you take it and you throw it, wasn't able to follow through there. Okay. As the ball rolls off my fingertips, it's about how high up in the air are my fingertips? About 8 feet. So that's where I'm getting the 8 feet from. Okay. If you're 5.5 feet tall, then the final distance might be about 7.5 feet, 7 feet 2 inches, something like that. But whatever it is. Okay, so that's where the initial height comes from. The initial velocity, the 60 feet per second, you can get that from a speed gun, can't you? That's easy enough to do. Okay, well the question is, how long until it hits the ground? 1. Okay. How long until it hits the ground? And then the second question we're going to come back to is, how high up in the air does this ball go? Well, one of the first things you may be wondering is, well, can a person really throw a ball 60 feet per second? Is it possible to throw it that fast? In 1 second's time, it's going to cover 60 feet? That's kind of like zipping right along there. Okay. To answer that, let's do a comparison. One of the things that I always remember, picked it up in a physics class, is 88 feet per second is 60 miles per hour. Is it humanly possible to throw a ball 60 miles an hour? Yeah. How fast do pitchers in the major leagues throw a fastball? Upper 90s, sometimes right around 100. Okay. So 60 miles an hour is doable, even for mere folks like us. Okay. So it's not an unreasonable speed. Okay. So let's put this in. How long does it take until the ball hits the ground? Well, I'm going to use my equation, negative 16t squared, plus the initial velocity. The initial velocity here is 60 feet per second, and you got to make sure to do things in feet per second and in seconds. Got to do feet in seconds, plus s sub 0. What's s sub 0 in this particular situation? 8. Got it. Equals. Now, here comes the tricky part. If we want it to hit the ground, what's its height going to be? 0. So we're going to set this equal to 0. That's when the ball's going to go thump and be back on the ground, a height of 0. Huh. Any ideas how to solve that? That's kind of a mess. Does it easily factor? Can you factor that in your head? Yeah, neither can I. We could divide by 4, right? And we get minus 15t squared, minus 15, minus 4t squared plus 15t plus 2 equals 0. Makes the number smaller, but no easier to get through. Do you happen to remember something like this? X equals the negative of b plus or minus the square root of, oh no, what's he writing down? The quadratic formula. Oh no, what did we just back into? You can use the quadratic formula under 2 conditions. 1, the equation is a quadratic. Is that a quadratic equation? Yes. Secondly, it must be equal to 0. If it's equal to 3, if it's equal to 4x minus 7, you got to move all that stuff back over to the left-hand side. It must equal 0. Okay? Won't work otherwise. Okay, a is that coefficient there, isn't it? So a is going to be a negative 16. B is going to be a positive 60. And C is going to be a positive 8. Now it's down to just doing what? Plug it in. So what we're going to wind up with then is x equals the negative of whatever b is, plus or minus the square root of b squared, so that's going to be 60 squared, minus 4 times a, that's a minus 16, times c is 8, all divided by 2 times this negative 16. Everybody okay so far? Yeah, but Chuck, I really don't want to have to mess with quadratic formula anymore. I wish it'd go away. Sorry. Okay, so this is going to give us then a negative 60 plus or minus something or other over a negative 32. This is going to be a square root. This is going to be 3600. Then we're going to have plus, right? Got a couple minuses there. And you have this 4 times 16 times 8 plus 512. So far, so good? Equals a negative 60 plus or minus the square root. This looks like it's going to be about 4112 divided by a negative 32 equals a negative 60 plus or minus something or other over a negative 32. Well, let's see. What I need to do is to take the square root of the 4112. This is going to be 64.125. I'll usually just take things out 3 decimal places, rounding off at the third. Okay. So unless we're using dollars and cents, which would go out how many decimal places? 2. You'd go out 2 for dollars and cents. Unless it's that, we'll just run it out 3 places. Now what? We're going to get 2 answers, aren't we? We're going to get one answer where we add the 64. So we're going to get one answer. We have a negative 60 plus 64.125 divided by a negative 32. And we're going to get another answer, a negative 60 minus 64.125 divided by a negative 32. If we work this first one out, do you see that it's going to wind up being a negative value? Because we're going to wind up with a positive 4.125 divided by the negative 32. And that's going to give us a negative 0.129. Then we have a negative 60 minus 64, so that's going to give us a negative 124.125 divided by 32 equals, and this works out to be a positive 3.879. Now, I accidentally, up here, put down x equals, but in reality, what's the name of the variable in this equation? It's t. So we should have t equals, and if we go down here, each of these values on the bottom line is a time, isn't it? What units is this in? Days, weeks, years? It's in seconds. Okay. Only one of these answers makes any sense. Remember, the question is, after you throw the ball in the air, how long is it till it hits the ground? Which answer does not make sense? Yeah, the negative one. That would mean it hit the ground before you threw it, right? It might have. You might have dropped it, or it might have fallen out of the glove. But realize that this answer doesn't make any sense. You mean it's okay to have answers that don't apply? Yep, there's one right there. The second question was, how high does the ball go? There are a couple ways to answer this. We have our height is going to be our negative 16t squared plus 60t plus 8. One way to do this is to use some calculus on it. Of course, that takes a couple of months of studying to get to the point where you can actually solve this using calculus. And some of you might be headed that direction. In fact, I'm teaching a couple of sections of calculus, and next week they're going to learn how to solve this. But we started that class when? Well, same time as this one, back in August, right? Holy mackerel, they got to get halfway through October before they can solve this? Yep. Okay, what's the other idea, Chuck? Keep in mind that when we graph this, this is going to be a parabola. Whoops. And it's going to do something like this. Right? Where this is time, and this is height. It hits a peak at that location right there. What's that location right there called? It's the vertex, isn't it? And we want to know at what time, first off. And once we know the time, we can figure out the height. How can we figure out the time here? Well, if you recall back, the vertex is at negative b over 2a. Does that look familiar from somewhere? Okay, the vertex occurs at negative b over 2a. Well, wait a minute. Negative b is 60. 2 times a is going to be 2 times the negative 16. Okay, so that's going to give us a negative 60 over a negative 32. Notice the time's going to be a positive value, isn't it? Does it make sense it would be positive? Okay. And if we take that and do 60 divided by the 32 equals, it's going to be 1.875. 1.875 what? Elephants? Feet? Seconds. It's time, so we're going to measure in seconds. Now, from there, we do need to get this in feet, don't we? Because the question wasn't at what time does it hit the highest point. It hits the highest point just under 2 seconds. The question was, how high does the ball go? Any suggestions on how to get that? Yeah, just don't make contact with Chuck and he'll tell us. Don't look at his eyes. He might call on you. You plug it into the formula. Well, we want to know to get the height, we want the height at 1.875 seconds. So that's going to be a negative 16 times 1.875 squared plus 60 times 1.875 plus 8 equals. Are you okay crunching that out on your calculator?
Is that a 5 up there? A 5?
This?
Yeah.
That's the S. So that means the height at 1.875 seconds. Yeah. Let's see what that works out to be. I'm going to press clear, get everything else off of there. I'm going to do negative 16 times 1.875 squared plus 60 times 1.875 plus 8. Is that about what you got on your calculator? And if you didn't do it, you may want to try it just to make sure it's working, because next week you're going to have a quiz over this stuff, aren't you? Uh-oh. Think something like this might make its way onto the test? Maybe. And this is going to be 64.25 watt. Is this the elephants? Feet. This is the feet. So what's the maximum height the ball achieves? A little over 64 feet. That's pretty good. That's about 6 stories. Does that make sense? How to work something like that through?
So when you plug it in, the S,
Okay, yeah. What S says is there's an equation laying around here somewhere named S. Oh, the thing named S is up here. So I'm going to plug it into this equation. So I do the negative 16 times 1.875 squared plus the next thing it says is 60 times 1.875. Then the next thing it says is plus the 8. So there's the plus the 8. Does that make sense? Everybody good with that? All right. There's one application with parabolas. And the cool thing about this is this equation, if we move up a little bit further, here it is. This equation's handy for all kinds of stuff. Really, Chuck? Okay. For example, a couple of years ago, we took the kids on vacation to Yellowstone. Go there someday. It's worth it. If you're driving from here, it's 3 hours, I wish. It's 3 days of driving, 10 to 12 hours a day. Please? That'd be nice, wouldn't it? Austin, that'd be a great place to hike. Okay? It's 3 days, 10 to 12 hours of driving a day. And it's not slow driving because when you get a little further west, the speed limits are a little different. Okay, the signs say 65 on the expressway. Okay, and I was doing a little faster than 65 because they were treating me like grandma or grandpa on the road blocking traffic. But I was afraid to go very fast. And we were filling up at a gas station and a trooper happened to pull in. And I figured, I'll just shoot the breeze. I said, I said hi. I said, they kind of drive fast out here. You know what he told me? Yeah, keep it under 100 and nobody's going to bother you. And I said, yeah, I was kind of noticing that, but I was afraid to do it. And he said, it's really dangerous to drive 65 out here. You'll get rear-ended. I said, yeah, I was kind of noticing that too. So on this 10 to 12 hours of driving, some of that is rolling miles. Okay, because you're 90, 95, 100 miles an hour. Okay. So anyway, long about day 2, we come up, we've crossed a whole lot of the prairies and stuff, and from the east, you're driving along, and I'm serious, it just drops off. And then down in here is the strangest looking stuff. It's kind of like muddy, baked desert rock. Looks kind of like what you would expect the moon to. It's called the Badlands. They were called the Badlands because back when it was just horses, it was bad land and you didn't want to get stuck in it because you would die out there. I mean, you would just bake and die. There's no water, there's nothing. Okay? So, okay, well, what's this have to do with anything? Well, we spend a day or so kicking around out there, and this area is huge, and no, they don't have handrails around the cliffs. They would need God only knows how many miles of handrails, and they're just trusting people to be somewhat intelligent. Okay? Well, the kids and I walk up to one of the cliffs, to the edge of it, and gosh, dang, that's high. Yeah, no kidding. That's really high. Okay? It's not fun until you're scared, right? So the kids and I are there like that. How high do you think that is? And you hear Becky screaming from about 25 feet back, get the kids away, get the kids away. We're fine, get the kids away. Okay? And they're there, how high do you think that is, Dad? And I said, tell them. I said, there's a real easy way to find out. And now they're intrigued and they want to know how. So I said, okay, let's slide our feet back and back away from the cliff a little bit. And there wasn't anybody down there in the bottom. Made sure of that first. There wasn't anybody near around down there in the bottom. And I told Daniel, pick up a rock. Well, the first thing he does is he picks up a small boulder. I said, no, a rock. Okay, so he gets something about the size of a softball. So I tell him to stand there and hold it out over the cliff. We're going to count 3, 2, 1, drop. And told Lauren to get out her cell phone, pull up the stopwatch. And I told her, as soon as we say drop, you press go and watch. Don't wait to hear it, but when you see it hit the ground, press stop. And then we'll know how high up we are. And the kids looked at me, really? Mom, okay? So, anyway, they go along with it because, hey, if you got a chance to throw a rock off a cliff, who's going to skip that? So they dropped the rock, and I made it very clear he had to drop it. He could not throw it. He had to drop it. So he drops it, and we see it hit. Boom. And I don't remember exactly what it was. It was about 4.17 seconds was the drop time. Okay? Which is a long time to drop. And I said, okay, now we know how high it is. Really? How are we going to do that? Well, you get out this equation that I just gave you. S of t equals a negative 16 t squared plus v sub 0 t plus s sub 0. Now, I was very careful to tell Daniel, don't throw it, drop it, because when you let go of it, what's the velocity the instant you let go of it? 0. That makes life really easy because this whole term goes away. Right? Now, we've got our time. What would we say it was? T equals 4.17 seconds. We can start plugging some stuff in. We got negative 16 times 4.17 squared. We have an initial height, S sub 0. That's where the rock started. Do we know what that height is? Nope, we have no idea what that is. But when it hit down here, now how high was it? 0. We're calling that 0. So we can call that height 0. Does that make sense? Oh, wow, this is getting like really easy, Chuck. Okay, so I told Lauren, pull up your calculator, turn your phone sideways, because when you turn it sideways is when you get all the cool stuff going on, at least on the one we had. And what we wind up with is S sub 0 equals a positive 16 times 4.17 squared. So we just worked that out quick like. 16 times 4.17 squared equals, and the kids freaked. How high up were we? It was high. It was noticeably high. And I got thinking, maybe Becky was right. How high up was that cliff that we were looking over? Almost 300 feet. That's like 30 stories. So this is about 28 stories high. But the point of this is, this equation that's now at the top of the screen can be used for all kinds of cool stuff. If you're throwing, if you're dropping, if you're hitting, if you're kicking, some kind of a ball or a rock or whatever it might be, there's all kinds of stuff going on. Now, that said, I'm going to tell you, don't do this on the Eiffel Tower, Kings Island. But Chuck said I could. Yeah, well, when you do that, what's the next move? Security grabs you and what? They drag you out of the park and kick you out. Please?
They're not a big fan of that.
Yeah. The throwing you out of the park or the
Dropping
dropping
stuff.
stuff off of the Eiffel Tower. Why don't they want you dropping stuff off of the Eiffel Tower? Yeah, what is it, about 330 feet?
Something like that.
The observation tower?
It's like a third of the Eiffel Tower.
Yeah, so, okay. So let's guess, just for grins, let's guess that it's 330 feet tall.
I mean, that sounds right.
Okay? Not quite sure. All I know is that they have roller coasters. I've been told they have other rides, but all I ever see is roller coasters. Okay? So we've got an initial height of 330, and we could figure out about how long it would. We're running out of time here. We could figure it out. It's going to be going close to 100, 120 feet a second. It's about 80, 90 miles an hour. If you get hit with something going 80 or 90 miles an hour, that's going to hurt. Daniel plays hockey. He gets hit with pucks doing 90 miles an hour, but he's got a heavy-duty mask on. If you hit somebody at that speed and they don't have a mask on, they're going to get hurt, depending on what you drop. Unless it's one of the stuffed animals. Anyway, so realize that there are different things that this could be used for. The equation, not the Eiffel Tower. Okay, let's take a look at something else here. When you've got a quadratic, okay, and what I'm doing now is I'm sliding into section 3.2. If you have a quadratic, something like y equals 2x squared plus 2x, let's say minus 12. One way to solve this is with the quadratic formula. It's not the only way to solve it. We could graph this. Yeah, that would mean reworking it to get it in the form, you know, where you have x minus something or other squared and all that jazz. Another way to do it is to factor this. Ooh. If we factor it, it's going to be 2x something or other and x something or other. And the two numbers here and here have to multiply to equal what? 12. Does that make sense to everybody? They got to multiply to give 12. This sign right here is negative, and that tells you something about these two signs. Are they the same, or are they the opposite signs? They're opposite. Okay, so we know it's either going to be a plus here and a minus here, or the other way around. That means that we're going to have the positive one number and the negative of another number that's going to have to add up to give us a positive 2. Everybody good so far? All right, so now we got to tinker around. What are some factors of 12? Well, yeah, 2 and 6, 3 and 4, and twice one of the numbers, because it's going to be multiplied by a 2, minus the other one has to give us a positive 2 back, doesn't it? Any ideas of which pair of numbers where twice one of them minus the other is going to give us 2 would work? Well, let's see. Twice 1 minus 12, that's not 2. Twice 2 is 4. And the 6. Oh, is that going to give us? It might work, depending on how we line it up. We can try it. Let's see. If we put a plus here and a minus there, is that going to work? We can experiment. It's going to give us a minus 4 and a what? Minus 4x plus 6x. Does that work? If you multiply it out? We're going to have a minus 4x plus 6x. Does that give us, excuse me, does that give us 2x? It looks like it might work. So we could try multiplying this back out. The firsts are going to give us our 2x squared. The outers are going to give us a minus 4x. The inners are going to give us plus 6x. Minus 4x plus 6x. It's got that, 2x. And the last is going to give us minus 12. All right. So it looks like that factors. Now, The thing to remember here is we are looking for roots. Roots means it hits the x-axis. If it's on the x-axis, what's the y value? 0. If we're looking for roots, that means this is equal to 0. Does that make sense to everybody? We're getting close. Good. We've only got 3 minutes. Better get close. That means this 2x plus 6 equals 0, or the x minus 2 equals 0. Why does it mean that one of those has to be 0? One of them has to be 0. Why? How do you know that? Because my teacher in junior high school said so. Well, think about, go back up a step here, and if we look at this line right here, you've got those two things being multiplied together, don't you? And when they're multiplied together, it gives you 0. Let's play a game. I'm thinking of two numbers, and when I multiply them together, I get 0. One of the numbers has to be what? 0. It doesn't work for anything else except this. Like if I said 1, there's an infinite number of numbers that you could multiply together to get 1. 2 1/2, 3 1/3, 4 times 1/4, 5 times 1/5. Oh yeah, that could go on forever. But to get 0, one of those two things has to be 0. This gives us then that x is equal to a -3, or x is equal to 2. Does that make sense? If you plug in this into that equation, what number is going to come out? 0. If you plug this into that equation, what's going to come out? 0. And this actually gives you some idea of what's going on with the parabola. This gives you the information that you hit the x-axis at -3. And you intersect the x-axis at 2. Now, the vertex is halfway between those, isn't it? So the vertex is going to be like here at a -1/2. And it's got to be somewhere down here. How do I know it has to be down there? It opens upward, right? The leading coefficient is positive. The parabola is going to come through -3, go up through 2, and it's going to look, pretend something like that, okay? But it's going to look something in that range. Does that make sense? Quadratics, especially with this equation that we were just looking at, okay, can take on all kinds of useful situations. Folks, remember to bring a calculator with good batteries in it Wednesday, okay? I'll see you then. I hope you have a good day.